Well, they're chilly old mornings in April, and we put the fire on. Even though there's a lot of light, it doesn't necessarily mean it's heated up very much. In the room here this morning, we can see that it's about 49. Yep, 49 on our Humboldt scale with good old Kelvin here. Well, how do we convert that? So if you set yourself a table up like this, where you've got the scales down the side, and I'm looking at our Humboldt scale, the centigrade scale, the Kelvin scale, which is based on the same divisions, that is 1 degree Kelvin is equivalent to 1 degree centigrade, except 0 in the centigrade is 273, approximately, just a little bit more than 273 Kelvin degrees, because Kelvin is based upon an absolute zero, the Kelvin zero, where all molecular motion ceases. Remembering, heat's related to molecular motion. And then Fahrenheit. Along the top I've got our reference points. RO was our body temperature, which on our scale is 100 and roughly 37 centigrade. R1, which was the room temperature. That's a warm room temperature, and you can see the comparison with today, which is a cooler day. There's a lot of fluctuation and inconsistency with the room temperature. Our ice water, which came out at 21 Humboldt, which is equivalent to 0 centigrade. Well, you can draw the graph. So here we have the graph of Fahrenheit versus centigrade. You could say 150 here Fahrenheit, and we just come up to the trend line, and then across here will give us centigrade. So somewhere here around just over 60, around about 70 degrees. We have the formula of the trend line, which gives us the relationship between Fahrenheit and centigrade. And if we take that formula and we put it into a spreadsheet here, we can use it as the translator, the converter, so our own converter. So we've put the formula in, and we can see that that formula takes Fahrenheit 0 and calculates it out as negative 17.8 centigrade. Remember, once you've got a formula in Excel, you can take that formula, make a little black cross, and just drag that down, and it'll carry the formula. We can use that to make a table, all right? So we could take Fahrenheit, and now we can just add into our table a series of numbers, and as soon as we enter that, it calculates for us what that is. We want it to. When you're using Excel, you can use this little square up here, and that can bring your significant figures down to something sensible. What level of accuracy can you actually measure? So we've done this here, over here. So we've now also, I can show you, we've taken the Humboldt and the centigrade. The two accurate measures we had were our body, 37 at 121 ice and water, and the graph gives us the formula here, the relationship between our invented scale and the centigrade scale, and then we can come over and we can see we've got a conversion chart here. We're sitting here, what did we say before? We just said we're sitting here at about 49, so 13.2, about 13 degrees in the room at the moment. Pretty chilly, pretty cool for the morning. Well, the room's warming up gradually. We're getting over 50 now. It's steadily warming, which is pretty good. And we've got our results now from our experiment we're putting in. The way I've put them in is distinguish between the different thermometers that we have. And along the top I'm recording air 1 litre, and I've got 3 repeats of 1 litre, 10 litres, 50 litres, and the C. And at different times, and then getting the averages from my replicates, and averages from the different thermometers. Now the water at the start all came at the same time, same place, And interestingly enough, it was in the morning, early morning, and everything was pretty much the same temperature. And then every 2 hours took samples, and you'll see that after the first 2 hours there's quite an increase in the air temperature and in the 1 litre, not such an increase in the 50 litres. I didn't do the C every time, and then I took all those time sequences and put them into a summary table, and you can see that I took 2 hours, 4 hours, 6 hours, 8 hours, 10 hours, and then overnight, basically it was 2 p.m, 4 p.m, 6 p.m, 8 p.m, 10 p.m, and then overnight, of course, did measure, and then in the morning again, took another measure. We can see the C didn't change at all in that time. You know, it's a big mass and pretty stable and not really showing any change. And we graphed this, and we graphed it over time. We can see that the purple line, which is the 50 litres, does not increase in temperature as fast as the green, which is 10 litres, or the red, which is 1 litre, and definitely not the air, and then loses heat at a slower rate into the evening. The horizontal blue line, which is the C, does not change at all, but then in the morning, down this end here, we can see that they've steadily lost heat overnight, and the temperature is lower, but not as fast. We can also graph, if you like, or calculate, if you like, the rate of change per hour. And there are formulas for this I just put in. So, for example, here, I just take the difference between the 2 hours and the previous time period, and divide that difference by 2 because it's 2 hours, and that gives me a calculation for the rate of change per hour. I think these two graphs clearly show us that as the mass increases, then the slower the heating process, the slower the temperature rises, and the slower it loses heat as well. Therefore, it's fair to conclude that the ocean, which is a large mass, has a more stable temperature over time than small pools of water. Well, the room's really warmed up now. The sun's come round and it's taken a few hours, but we're now at about 61, or just over 60 Humboldt. Now, as we can actually do some calculations using some heat formulas as well. And we've got specific heat, which is unique to the material or substance, and you can see the specific heat, that is the joules of energy per kilogram in degrees centigrade, is 4182, and for seawater 3850. There are reasons for that which we won't go into, and we got over here the temperature shift in the first 2 hours of our experimental situation. And if we use a formula of the mass times the specific heat times the change in temperature in degrees centigrade, we can work out the thermal heat change in joules. And here we can see that the amount of heat absorbed into the 50 litre container, even though it didn't increase in temperature as much as the air or the 1 litre or 10 litre, the amount of heat is actually far greater that's built up than in the smaller volume. And the total amount of heat is calculated in Kelvin, so it relates to absolute zero, and the formula is simply the mass times temperature in degrees Kelvin times the specific heat capacity, and we can see that the total heat stored in that 50 kg is far greater than the total heat stored in the other two containers. So this relates to the relationship between the mass or the volume and the storage of heat and heat energy, and how the ocean has become or is a thermal store, a thermal sink, has huge heat capacity, and being stable over time, that means the temperatures near the coast stay more stable, and that heat that was accumulated in spring and summer is gradually released through autumn and winter, and so therefore in winter time we have milder temperatures, but at the same time it doesn't heat up as much in spring and summer, so therefore stays cooler than the surrounding air and land in spring and summer, so coastally it's cooler in those seasons.